Okay, welcome to section 9.6, vectors in space. This is going to be similar to what we did in two-dimensional vectors with x and y's, but this one is going to be three-dimensional. So we've got x, y, and z. Here's my x-axis, positive y-axis, and positive z-axis. And a vector such as this means go 3 units in x, 5 in positive y, and then up 2. And that's approximately where I said it would end up. This next vector, 4, -3, -2, positive 4 in x, 3 in y, and then down 2 in z. So again, you can see drawing them is very difficult, at least if you have limited artistic talent like I do. But I just want you to be able to visualize what's going on. This vector is -3 in the x direction, positive 5 units in the y, and -4 in the z. Again, that's approximately where I would like to draw it. And then we have one more here. In each one of these, we're drawing z. Okay, just like in two-dimensional vectors, we can find the magnitude of a vector v, but we can also break our vectors down into components. So this vector 3, 7, 4 means that we've gone 3 times the unit vector in the x direction, 7 times the unit vector in y, plus 4 units in the z direction, with k being the unit vector in the z direction. And to find the magnitude of that, we simply take the square each component, add them together, and take the square root. So we have 3 squared plus 7 squared plus 4 squared, giving us the square root of 74, so approximately 8.602. And if I have 2 points that are given to me, the way I find the magnitude of the vector that goes from A to B, and we designate that by putting this little symbol above it. So from A, that's my tail, to the head of the vector, B, is the x value of B, the x value of B minus the x value of A, point A, times unit vector I, plus the y value of the point B minus the y value of point A times the unit vector in the y direction, J, plus the z component of point 2 minus the z value of point A times the unit vector in the z direction. And this makes sense. Just the distance, how we find distance on a graph. So we have -4i minus 5j minus 4k. And again, to find the magnitude, we square each of those values. So -4 squared plus -5 squared plus -4 squared, add them together and square root them, and we have the magnitude, or the length of vector AB is approximately 7.550. Okay, turning over. And again, I apologize, I'm just trying to talk you through these. If I want to find the distance between the following points, so going from point 1 to point 2. So again, point 1 is the tail, point 2 is the head, where we finish. So I take the ending x value minus the beginning x value times vector I, plus the ending y value minus the starting y value times vector j, plus the ending value for point in the z direction minus the starting value in the z direction times the unit vector in the z direction. And then to find the magnitude, I just square each of those, add them together, and square root it. So I get 7.61. Okay, so we want to be able to do similar things. Adding, subtracting, all of those things that we've done with two-dimensional vectors, we can do with three-dimensional vectors. So if I want to add two vectors together, I simply add the I components together. If I want to subtract two vectors, we take the x component from x component from V minus the x component from W. times vector I. Take the y component from vector v minus the y component from vector w times unit vector j. Oops, I missed the little hat there. And finally, the z value from vector v minus the z value from vector w times the unit vector in that direction, k. If I want to multiply by a scalar or by an integer, I simply distribute that 3 to each component of my vector v. And there's my new vector. I could do the same thing where I multiply vector v by 2, multiply vector w by 3, and I'm going to subtract 3w from 2v. So I've multiplied vector v times 2, and then I've multiplied each component in vector w by negative 3. And then I'm going to add those together. So for instance, here I would have 6i. Here I would have a positive 6i. Added together gives me 12i. And the magnitude for the vector, I just want vector v, so 3 squared plus 5 squared plus negative 2 squared, square rooted. And here's another one for you to do just to practice, then double check your answers. But same way we've done it with two-dimensional vectors. Okay, unit vectors. So again, just like in two-dimensional, we can have a unit vector. So it is a vector that is going in the same direction as the vector I'm given, but the length of it or the magnitude of it is just 1. So the way we get that is we take our vector, find the magnitude, so x component squared plus y coefficient squared plus the z coefficient squared, square rooted. So I got the square root of 29. And then I take that original vector v and divide each part of it by the square root of 29, by its magnitude. So the new vector, the unit vector in the same direction as v, is negative 2 divided by the square root of 29 times I, plus 4 times the square root of 29, plus 3 times the square root of 29 times k. If I'd wanted to find the magnitude of this now, the magnitude of this is going to give me 1. That is the whole goal. It's a unit vector, so length of 1 in the same direction as vector v. Here's another one for you to try on your own. Find the magnitude of vector v, and then divide each component by that. And there you go. Okay, let's continue on, finish off these notes. We're going to talk about the dot product. How does that work with three-dimensional? Same way it worked with two-dimensional, except here we're going to have to multiply the I components together, so 2 times 3, the j components together, 4 times negative 1, and then the k components together, negative 3 times 5. And remember, we just get a scalar. We do not get a vector when we do a dot product. Here, I'm multiplying them in a different order, so vector w dot vector v. And notice that we get the same value. Vector v times vector v. And we can certainly do that. Likewise, vector w dot vector w. And there's the value we get. The magnitude of vector v, the x direction squared plus the y unit squared plus the z value squared. Add them together and square root them. And there we did the same thing for vector w. So now let's give it a shot yourselves. So pause this. You're going to do v dot w, w dot v, v dot v, w dot w, the magnitude of v and the magnitude of w. And keep in mind, you may have noticed this up here, that the dot product of a vector with itself is just the same as the magnitude squared. So the square root of 29 times the square root of 29 gives me 29. So the magnitude squared gives me the result of the dot product times, or the vector dotted with itself. Okay, how to find an angle between two vectors. So this is a little bit more detailed. I first have to find the dot product. So here's my formula. The cosine of the angle between these two vectors is the vectors dot together divided by the magnitude of the first vector multiplied by the magnitude of the second vector. So at the top, I've got the dot product. Here is the magnitude of vector u, the magnitude of vector v. Do the algebra involved here, and we get cosine of -6 divided by the square root of 38. So to find that angle, I now have to do cosine inverse of this, and I'm going to look for an angle in degrees. So make sure your calculator is in degrees when you do this. Notice I didn't take time to rationalize that because I'm just using this as a temporary step to insert it into find cosine inverse. Here's the second one. Again, we've got vector u and vector v, and I want to find the angle between them. So I take the dot product of u dot v divided by the magnitude of vector u times the magnitude of vector v. And again, this is simply plugging in numbers and doing the arithmetic. So we get cosine of -7/7 square root of 30. Take the inverse cosine of that, and we get a degree of 116.3. Okay, there you go. You have that. Good luck on the homework, and feel free to ask us if you have any questions.